Welcome to example number 3, the sine and the breaking chord. So we have a uniform beam of weight 196 newtons and a length of 1 meter that is hinged to the outside wall of a restaurant. There's a cord here that is attached to the center of the beam, which is attached to the wall, and it makes an angle 30 degrees with respect to the beam. The cord keeps the beam perpendicular to the wall. And we're asked that if this cord has a breaking tension, a maximum tension of 620 newtons, what is the largest mass that we can have for a sine without breaking this cord? So the first step is we're going to pick a body that's in equilibrium, and that would be this beam right here. So we're going to apply the sum of the torques and the sum of the forces being both equal to 0 for this particular body. So we're going to need to draw a free body diagram for this beam showing all of the forces at their points of application. So along this rope here we have the tension, which I'll label as capital T, and the sine is pulling down here with a certain force that is equal to the weight of this sine, which is really just m times g. And then the beam is not weightless, right? We're assuming it does have some weight, and it states that it's a uniform beam, which means the mass is uniformly distributed over the beam. So essentially the center of gravity is in the geometric center of this body, which is in the dead center here. So right here at 0.5 meters, we have the weight of 196 newtons. And we also have forces acting here at the hinge, otherwise this beam would slide in to the left here. So there must be some horizontal component of that force, and there could be some vertical component either up or down. So you're just going to have to make a guess to what direction it is. So I'm just going to make a guess it's kind of like over here at some angle. And that's the force from the hinge, so I'm just going to call that maybe H for the force of the hinge. I don't know the hinge force. This is unknown. I don't know the weight here. That's unknown. I do know the weight of the beam. And I do know that this tension, the maximum value is 620 newtons. And since we're looking for the maximum mass that the sine could have, we're going to need to be using the maximum tension. So we're going to assume that this tension is 620 newtons. Now that we've drawn the free body diagram acting on this beam here, we can go ahead and then start thinking about the torque and force conditions, but actually see some forces that are at an angle. So I think that we should take this tension here and break it up into components. So the tension in the x-axis, along our x-axis, so I'm assuming, by the way, our chosen convenient coordinate system is an x to the right and y being positive. Our tension along their x-axis would be T times the cosine of 30 degrees. So that's 620 newtons times the cosine of 30 degrees, which is root 3 over 2. So this actually comes out to be exactly 310 root 3 newtons. And our tension in the y direction would be T times the sine of 30 degrees, which is 620 newtons, multiplied by the sine of 30, which is really a half, and this gives you 310 newtons. Now, if we were to apply the force condition, the sum of the forces equals 0, we'd find that you would have a tension in the x direction going left, so that's negative, and then you'd have it being counterbalanced by the hinge force in the x direction. And these two forces, well, I guess you could find the hinge force in the x direction, which would be T times, well, actually I already know that value. Tx is actually 310 times root 3 newtons. And this is approximately equal to 537 newtons. But this wasn't asked actually in the problem, but good to know anyway. So the x component of this hinge force is equal to the x component of that tension force, and that hopefully makes sense. It's not because all the other forces either going up or down. Now if we sum the forces along the y-axis, we'll see that we have a y component of this tension, Ty. We have a y component of this hinge force, h sub y, and then we have these two other forces. So you would have tension y minus the hinge force in the vertical direction minus W minus mg equals 0. And then you could put the 310 in here, but you don't know the hinge force in the y direction, minus W, we know actually, that's 196 newtons, and then minus mg equals 0, but you see you have two unknowns because you don't know what angle this hinge force is acting at, so you can't really find this hinge force in the y direction. So you're kind of stuck here. So you're going to need to apply a torque condition, and that's what's going to get you the answer here. Now remember that it's going to make your life a lot easier if you pick a torque about a pivot point where you have unknown forces. Where do you think would be a good location to put your pivot point? Well, hopefully you're thinking right at the hinge because you don't know these forces. Well, you know the x component, but you don't know this force. So I would say this would be a good point. I'm going to call that point P. So now applying the sum of the torques about point P equals 0, we're going to be looking at all the individual torques. Now the torque from this force H is going to be 0 because it's right at the pivot point, and so the position vector is 0. So we really only have the torque from the wire, the tension. We have the torque from the weight of the beam, and we have the torque from the weight of the sign. And all of these torques will balance out to give you 0. The torque from the tension is going to cause the beam to rotate in the counterclockwise direction. The torque from the weight is going to make this beam swing downwards, which would be going in the clockwise direction. And the torque from the weight of the sign will also go in the clockwise direction. So these two torques, since they're both in the clockwise direction, are considered negative, and the torque from the wire is going to be considered positive. So this is a positive torque. We have a negative torque here and a negative torque here. And all of these balance out to be 0. So now let's substitute in our magnitudes of torques, force of tension, or actually maybe we should be using just T. So it's T for that force. Then multiplied by the distance from here to here. I'll just call that for now R sub T. And then multiplied by the sine of the angle between this tension and the arm. The position vector here, which is a 30-degree angle. So it's the sine of 30 degrees. And we have minus the torque produced by the weight, which would be W, that force, multiplied by the distance between P to that point of application. That's R sub W, we'll call it. And then multiplied by the sine of the angle between this force vector and the arm vector, which is really just 90 degrees. And sine 90 degrees is just really 1. And lastly, we have the torque produced by the weight of the sign. So that's m times g, that's this force, multiplied by that distance. I'll just call that subscript r sub g. And then multiplied by the angle between the position vector and the force, which is really just 90 degrees. So sine of 90 degrees is 1, and all of this will balance out to give you 0. So now let's substitute in. We're going to put in our maximum tension of 620 newtons. Now R sub T is the distance from the axis of rotation to the point of application of that force, and that is 0.5 meters. So we're going to put in 0.5 meters. Sine of 30 is really just 1/2, and minus the weight of the sign, or the weight of the beam, which is 196 newtons. Then times the distance, and it's the same distance as before, 0.5 meters, because it's at the same point of application. And then the sine of 90 is just 1, so I'll just leave that there. And then mg, our unknown. And then r, which is this distance right here from the point of application to the axis of rotation, which is 1 meter. In fact, I probably could put in g in here. So all you're doing now is just, solving for m. So you have 9.8 m on the right side. I'll just bring this whole term to the right side here. And then 620 times 0.5 times 0.5 gives you 155. And the 196 times 0.5 gives you 98. So 155 minus 98. It gives you a weight of 57 newtons, which is equal to 9.8 m. And so m turns out to be 5.82 kilograms. And that's your maximum weight of the sign. And there you go. But you know, you could go a little bit further and find both the vertical and horizontal components of that hinge force. We've actually figured out the x direction of that force. We could find the y one. Let's just do that since we're almost done with that. So we're going to put 310 minus the vertical force of that hinge minus 196 minus this weight, which is 5.82 times 9.8. And this is, I'll just put that on the right side, equals that. And it turns out that that hinge force, the vertical component of that hinge force, is 57 newtons. And so you could actually find the resultant hinge force by simply using H equals the square root of the x component squared and the y component squared, which gives you a magnitude of 540 newtons. And you can figure out the angle by doing the arctan of the y component over the x component. And that works out to be about 6 degrees just below the horizontal. Okay, and that's it for this example.